Alright, let's briefly go over the E1 and Sn1 pathways. They're not too complicated because they go off of a lot of the reactions you've seen so far. So the difference between the E1 and the Sn1 pathways, in contrast to the E2 and the Sn2 pathways, is you'll see that they are not concerted. So let's start with an example. Say we have this. So the first thing you should note is that we have a tertiary electrophilic carbon, and you should note that the molecule we're using as both the solvent and the nucleophile is a weak base and a pretty weak nucleophile. So one of the prerequisites for an E1 or an Sn1 to happen is that E2 and Sn2 are much less likely to happen. So some things that help that occur are the fact that this is a tertiary carbon, which means Sn2 literally cannot happen, and because H2O is both a weak base and a weak nucleophile, E2 is very difficult to happen. So under these conditions, the only thing that can happen is this. So the first step is always going to be the spontaneous leaving of the leaving group, and I'll just say this is a spontaneous and rare event. Okay, so why is rare in quotes here? So you have to imagine that you have millions of molecules just hanging out in your beaker there in the lab when you're trying this sort of reaction. It's only on a rare occasion that the spontaneous leaving of bromine will actually happen. So that might mean 1 out of 1 million molecules, 1 out of 10 million molecules, what have you. But if you wait long enough, the spontaneous event will happen often enough that you'll get significant, push toward an E1 or an Sn1 reaction to happen. But in the Sn2 and the E2 reactions, you saw that there was donation into those anti-bonding orbitals, which forces the reaction to take place. But here, this bond-breaking event right here is pretty much the result of, well, one, solvent molecules playing with the charge here on this molecule, and the contortions and configurations of this as it moves through space. So occasionally, charge will build up in such a way that this bond will break. That's also one good reason why you need Sn2 and E2 to be heavily disfavored, because this spontaneous bond breaking event is quote-unquote rare. Okay, now that the carbocation is formed, the weak nucleophile could add on. Because the carbocation is such a good electrophile, you don't even need a great nucleophile to add. And H2O is a particularly bad nucleophile because it's a neutral species, but it has lone pairs, so it's able to add easily onto the carbocation, and you'll get this. Here you should be familiar with dealing with this sort of species from the electrophilic addition chapter. You are simply going to take the rest of the protic solvent and perform the deprotonation on this incoming nucleophile that just added. Once that deprotonation is done, you will have generated H3O plus in solution, and you will also have this new alcohol that formed. So this pathway is a substitution pathway because we started with bromine and we eventually ended up with an alcohol. So one functional group was substituted for another functional group. So what are the takeaway points? Well, first of all, the Sn1 mechanism, as I said before, is not concerted. And we know it's not concerted. Well, the existence of this and the existence of this. So these are intermediates. If you remember a concerted pathway, that goes through a transition state directly to products. You have no actual long-standing intermediate that exists. So it occurs through a carbocation intermediate, which hopefully by now you are somewhat used to dealing with. What that means is that we're going to see the potential for rearrangements during the Sn1 or E1 mechanisms. And we need to be careful whenever we're doing the mechanism that we account for hydride shifts or alkyl shifts or any of that jazz. The rate of this reaction depends purely on the substrate. So again, it doesn't depend on the strength of the nucleophile. If the nucleophile is strong, that pushes it toward an Sn2 or an E2 pathway. But since the rate determining step is how rare or spontaneous this bond breaking is, right? Once we form this carbocation, it's rapidly intercepted by the nucleophile, and then this deprotonation is also rapid as well because there's solvent molecules all around here. This is the slowest step in the mechanism. The slowest step is often referred to as the rate determining step. So when we're looking at the overall rate of the reaction, we say it only depends on the substrate concentration. If you have more substrate around, you have more molecules that could potentially undergo this spontaneous bond breakage. That's where Sn1 gets its name from, since the rate law, which is this equation, only has one concentration in it. It is first order. So the exponent here is 1, so there's something else here, so the order overall is first order. Okay, so also note that there's no great entropic driving force here because we took one group and we switched it for another group. Right, at the beginning we had, well, this molecule, and at the end we have this molecule. We also have H3O plus that we generated, but again, that's already in a solution of water. So there's no great entropic driving force in this sort of reaction. Okay, well, what if we look at this instead? What if we do the same reaction, but we do it in heat? Okay, well, I'll tell you that pushes things toward the elimination pathway. So the elimination pathway through E1 follows the same exact starting steps. You have this spontaneous bond breakage occurring, creating the carbocation intermediate, and then once you have the carbocation intermediate, you have the water act as a weak base, do the deprotonation here, which will result in the elimination product. Okay, so again, requirements: weak nucleophile, weak electrophile. Heat helps favor this over Sn1, right? If the solvent is ever present and you're doing an Sn1 mechanism, then there's tons of solvent molecules around here to immediately add. You need some sort of good reason for why this will eliminate instead of go through substitution. And the reason for that is the heat. The better reason is that elimination reactions are typically favored entropically. We talked about that at the same time we talked about the E2 reaction. So if you look at your free energy equation, if elimination reactions are favored entropically, then increasing the temperature will lower the Gibbs energy. And remember, a negative Gibbs energy is a spontaneous reaction. Okay, so what else do we know about E1? Well, we know a lot of similar facts. We know that it's not concerted, right, because we have the existence of a carbocation intermediate. Concerted pathways only have a transition state. This has transition states and carbocation intermediate. So just like with the Sn1, we see a lot of similar facts. The rate is going to depend on just the substrate, because again, if this is a strong enough base, it would go through an E2 pathway if possible, but it really depends on the rate determining step, which is this, and it's the spontaneous breaking of that bond. So again, this only depends on the substrate, so it's a first order reaction overall. And the other thing I was mentioning before is elimination is favored by heat, and when possible, you will be forming the Zaitsev product because that is the thermodynamic product. Okay, so now you know pretty much everything important that you need to know about elimination reactions. The other thing that you'll often be asked is to draw a reaction coordinate diagram. So here I've condensed the steps into very tiny representations of what they were before. This was the Sn1 pathway we just went through, and this is the E1 pathway we went through. So in generating a reaction coordinate diagram for the Sn1 pathway, remember that the y-axis here is always going to be energy, and then the x-axis is what we call the reaction coordinate. This will be reactants. This will be product. Over here, you see that this is your product, so you know you have at this step and this step an intermediate. The first intermediate you form, remember those are always the smaller valleys in your reaction coordinate diagram. This is the first intermediate over here, and this is the second intermediate over here, as you're slowly going downhill until you finally reach products at a more stable energy level. Of course, we're assuming this is going to be exothermic. So these, I guess, peaks over here are your transition states. This is transition state 1, transition state 2, and transition state 3. Remember, a concerted mechanism just has a transition state, but this is not a concerted mechanism because it involves intermediates. For E1, it's very similar. You see that you have your product over here and just one intermediate, so there is going to be one value that you have to worry about. Your intermediate will be here. Okay, so now you should try one of these problems on your own. So pause the video and predict the product of this reaction and draw me the mechanism. Okay, assuming that you gave it a try, the first thing that happens is because methanol is a weak nucleophile and a weak base, SN2 and E2 are not likely to occur. So instead you'll get the spontaneous leaving of bromine to generate this carbocation. You'll notice that this is a secondary carbon and the adjacent is tertiary, which means that there is a CH bond that could be used for a hydride shift to make this a tertiary carbocation. At this point, because we don't have heat and because the solvent is all around us and weakly nucleophilic, the Sn1 pathway or the Sn1 pathway is dominant. So the methanol will add. And once it adds, it'll have a positive charge, so you must do the typical deprotonation step that you do to get the final product, which is going to be an ether. Okay, so now I want you to predict the product and draw the mechanism for the same reaction, but this time we are doing it in heat. So pause the video and give that a try. Okay, let's take a look at it. So once again, methanol is a weak nucleophile and a weak base, and this is a secondary electrophilic carbon. So it's likely that SN2 and E2 will not be dominant. You'll go through the exact same steps as the previous mechanism in generating that carbocation intermediate, but this time the heat favors elimination. So what we'll have is the deprotonation adjacent to this carbocation, which will give us our double bond in our product. And once again, how about you pause the video and draw a reaction coordinate diagram for the energetics of these two mechanisms. Alright, I'm going to assume you gave that a try. So what I have are these two. So here on the left, this is reactants, this is products. You see you have 1, 2, 3 intermediates, so I have 1, 2, 3 values over here. Over here, this is products. I see I have 2 intermediates, so I have 1, 2 values over here. Okay, next up, give this mechanism a try. So pause the video and give it a shot. Okay, so once again, we have a weak nucleophile, weak base. We have a secondary substrate with resonance. Right, so what will happen is first the chlorine will leave and it will generate a secondary carbocation that can resonate to the left with that pi bond. So if we look at that resonance structure, what we'll see is that it allows the carbocation to get over here to this carbon, which is going to be adjacent to a tertiary. Once again, there's a CH bond over there, which will allow for the hydride shift to occur, generating an even more stable carbocation intermediate. Once this carbocation intermediate has been generated, because the solvent is all around us, the Sn1 pathway will be dominant. And we'll go through that same series of deprotonation steps to our final product. Remember, if you're at a carbon that can become a chiral center, in the case where you have a carbocation intermediate, since it's planar, the water could add the top or the bottom, giving a racemic product in most cases. Okay, once again, you probably saw this coming. Try the reaction in heat. So pause the video and give it a go. Okay, I'm going to assume you tried it. So once again, most of the steps are incredibly similar. So you will generate the same carbocation as the last time, which will be this one, but then you must choose what the Zaitsev product is going to be. You could put the double bond here, or you could put the double bond here. The difficulty is that if you put the double bond here, you see you have 1, 2 R groups. If you put the double bond here, you'll also have, well, 1, 2, 3 R groups. So that makes it rather obvious. But there's one additional reason why putting the double bond to the right is preferable. What you do by doing that is you generate this over here. So these are called conjugated double bonds, which are even better for resonance. You'll probably learn more about that in the next few chapters. Okay, so now try this problem. So pause the video and give it a shot. Okay, I'm going to assume you tried it. The first thing that happens is the same thing that happened in the previous problems. The bromine will leave, giving the carbocation one spot off of the strained ring. So what happens is you'll get the ring expansion to generate this carbocation, and then, since this is a secondary carbocation, you could do a hydride shift over to the tertiary location. And then lastly, now we finally let the nucleophile add the substrate and do the following deprotonation to this final product. And you probably expected this. Now I'm going to ask you to draw the reaction mechanism as if the system was heated. So pause the video and give that a try. Okay, so just as in the previous problems, the same exact steps get you up through the same carbocation intermediate, which will be over here. And the good part about E1 is that you don't need to worry about if this beta hydrogen is anti-periplanar or not, because it'll be able to, through the chair conformation or the chair flip, be able to get into a position where it'll be favored for elimination. Okay, so that'll do an axial grab there, giving the substituted double bond here as your Zaitsev product. Okay, hopefully that cleared some things up.